Hello community! Today we look at the grokked RAG. And you know what? Today is all about you, because after 3 videos of grokking LLMs and structured grokking and so on, I decided it is time to answer all your questions. So here we go. Here are your questions. What is RAG? What is the latest on RAG? When to RAG? How to RAG? Have you noticed that I don't like RAG? And then finally, there was the last question. What is grokked RAG and is it possible, and why we don't have grokked RAG right now? I feel like a frog pronouncing this, but okay, those are your questions, so I'm here for you. Let's start. The first one is, what is RAG? Now, a very simple question, maybe not that easy to answer. But hey, I accept the challenge, so let's start from a green grasshoppers. What is RAG? Now, RAG is some old technology. And here you see the importance of RAG today. And if you see here on the left side, yeah, there's a new technology. It's called Grog Transformer, but never mind. You see the dominant technology of today. Now, RAG is easy. It stands for information retriever. When the query then is augmented with relevant additional data from a vector store, and then the LLM generates an output. So we have 3 steps, no? Well, let's have a look. So the first step for the RAG is, of course, a data collection. You got a large corpus of documents, of text that is relevant to what you want to achieve, papers, articles, web pages, you copy the internet, respecting all the intellectual property rights, and then you clean and you pre-process the text data. You said, why you have to clean the data? Well, maybe your OCR brings back this, There are some problems in the text, so you have data collection and a pre-processing of the text data. Now, the second step you think is easy, no? It's the embedding. So you need now a pre-trained transformer model. In my days, it was a sentence transformer like SBERT. Today, you can choose here Mistral, Opus, Gaia, whatever you like. You just pay a little bit for it. And then you convert here the chunk of your text into some dense vector representation, which we call the embeddings. Remember, those text chunks, you have to define the length and you have to optimize it, but those are only details. So text comes in and you have here your pre-trained transformer. Now, since this is a pre-trained transformer, this transformer has been pre-trained on a particular set of data. And from this particular set of data, you defined the size of your vocabulary and you defined here which tokenizer you want to use for your pre-trained transformer. And now this tokenizer is really important because for each text chunk that comes now in, it uses here the mean pooling of the token embeddings from the last hidden layer to get you a single vector representation for this particular chunk of text that you decided this is it. So you see, interesting. Yeah, if you want to see this, there's a video, it's called SBERT 49. And there you have it explained it in all the beautiful details. Now, there could be the first problem that we encounter. Because if this pre-trained transformer and the text that this transformer was pre-trained on, where the tokenizer decided on the vocabulary and so on, maybe this was from a different domain than what you have in your data collection today. So maybe the vocabulary is a completely different domain-specific vocabulary to your data, so you have to be careful and check. But no problems because LLMs are pre-trained on a large corpora and can capture complex language patterns and semantic meanings. This is what you read in all the literature. And there's an easy solution, no? You pay, let's say, for GPT-4 embeddings here, since this is an all-domain pre-trained LLM. GPT-4, let's say, borrowed here the internet, respecting, of course, all legal requirements. So you see, if you don't know what to do, you find in the literature, just go with the most expensive, with the most including one, and then there should be no problems, no? Now, the third step for RAG is a simple one, a vector store creation. Because once you have those embeddings of your text chunks that you want to have here as your main corpora, the next step is to create a vector store that supports here this beautiful fast search. And this is the main reason why you build a vector store. Efficient similarity search. Now, let's go here for a popular choice. This is Elasticsearch. So what do? You define an index mapping in Elasticsearch to include a dense vector field for storing those embeddings. And then you just index the documents along with the embeddings into Elasticsearch. Now, the fourth step of RAG is simple. The search itself using here the vector field. Now, what is the most simple thing? You have a nearest neighbor search using the dense vector field to retrieve similar documents that you find if you have a query. And you see, code is as simple as that. Beautiful. And you know what's good? If you find here your particular cloud provider, may it be AWS Cloud, Google Cloud or Azure or wherever you are, it is available all over the cloud and the pricing is specific to your cloud provider. And now you see where this I don't like RAG is actually focused on. Because venture capitalists and all kind of investors about 2 years ago started to invest hundreds of millions of US dollars in those new vector store startups. And the business model of a VC is simple: to make profit, to make huge profit. 1 to 10 or 1 to 100, depending on what they invested. So for the rest of this video, I want that you imagine, whenever I say the word vector store, that there's this money of investment that you, the user who use vector store, you have at least to scale up 10 times, maybe 100 times for those investors and venture capitalists. And you see where we went now from science to a beautiful business model. Now, what is the fifth step for RAG? This is easy, no? We have now the query embedding here and the actual similarity search. So when the LLM encounters here my prompt or my query that requires, where the LLM decides, hey, I need additional context to answer this, it first converts the query into an embedding, a vector representation, using the same transformer model used to create the document embedding. So here again, we go to a very specific LLM, and you are allowed to pay for all the tokens, plus you're allowed to pay for the vector store. And the generated query embedding is then used to perform here this beautiful similarity search in the vector store, and you can go with whatever vector store you would like to pay for. Now, what is the sixth step here of RAG? It is the retrieval. Now, using the instances of the retrieved embeddings, we now fetch here the corresponding chunk of documents or chunk of text or passages from your original text corpora. And then, normally, you know, I've had my videos here, you take about 200 to 400 of the nearest embedding here to the query that you have, because otherwise you have a chance that you simply miss out on the correct solution. And yes, you can pay here for a good information retriever, because this is now step number 6, the retrieval of information. So now you have 400 different answers to a simple query, and the vector store just provided you 400 different answers. And now what you have to do in step number 7 of RAG, you have to apply a re-ranker, or as we do today, multiple re-rankers. Now, a re-ranker is normally a more sophisticated LLM, or as I use it, still a sentence BERT-based model. And the re-ranker takes now all those 400 documents that came back from the vector store and re-evaluates all 400 of them to pinpoint, fine-tune, it might be not the perfect word here, to pinpoint here the, let's say, the first 100 good answers. You see, and then you do a multiple re-ranking and you get the idea. And this re-ranker scores here the relevance of each of the 400 retrieved documents with respect to my query. Now you completely depend on this most sophisticated LLM model that is able to detect here the correct answer for a causal reasoning problem out of the 400. Now, here, simple code example here. You see here, I still go with cross encoder. You can have here this beautiful thing from the sentence, from the SBERT, from the sentence transformer, or you go to an LLM, or you go to a graph neural network. You have all the possibilities for your decision, which of the 400 are the best ones. If you want to learn more about the cross encoder semantic search, the code implementation, this is a video from 2022. But I told you this is also something new about research, and here we have from the end of May 2024 from Google Research and UCLA the latest research for improving your RAG system. And now really the latest is a graph-based re-ranking system. And you might say, isn't this fantastic? We have even a more complicated re-ranking because the vector store is giving us just 400 solutions, makes blah, and now we have to do the work outside of the vector store. And how it is done? Yeah, by the way, it's called here GRAG. No, this is perfect marketing, GRAG. Do you have your GRAG today? And do you have your AMR graph? And I had no idea what it is. And then I learned here, it is all about that you build a graph, but you do not build any graph of these documents that you have, but you build an abstract meaning representation graph. Now, I have to tell you, I'm not a linguist. I'm a theoretical physicist. So I ask here GPT-4, what is AMR? And I learned, introduced by a group of researchers here in the early 2010s, it is a standardized human-readable graph-based representation of sentence semantics developed by linguists before all the AI hype set in. And the most foundational paper is here, Abstract Meaning Representation for Embedding in 2013. And you see here, beautiful, and they created here, the linguists created here their own language. They took a large corpus of sentences and they manually annotated it with their individual AMR representation, which is of course great. And then they generated graphs of this. And you see, linguists, amazing capabilities. Now they have a specific formalism developed with the node and the edges, but careful, this is not graph neural network, with some rooted directed graphs, and then AMR just abstracts away from the surface form of the sentence, focusing on the underlying semantics as perceived by specific humans who evaluated this. And if you want to have here an example, here you have exactly the sentence is, she gave him a book, and here you see this new language, this new code representation of AMR. And yes, from this representation, you can build now a graph. So the linguists developed here a specific tool, and now the computer scientists come in for their AI and say, or tell the linguist, hey, give us your AMR graph, maybe it will help us. So we are still here in the 7th step for RAG, the re-ranking. But now we are not here of a BERT or an SBERT or an LLM, but now we have a GRAG. But remember, GRAG, to be specific, is just a very specific part in RAG. The 7th step here, it is an ARM re-ranker only, and it is based on the graph neural networks. And remember, AMR is a semantic representation language. And reading now here this paper, I found out that the information given by GPT-4 was incorrect because this refers back to 1998 as a derivation from the pattern and sentence plan language. So it is much more complicated in the historic development. If you are into semantic, if you are into linguistic research, and here you see here, I think this is page number 3 of the document, where I tried to understand what is happening within AMR. Okay, now you know the latest research, just 1 week old, if the perfect re-ranker according here to the latest scientific research. Now we come to the 8th step for RAG, and this is simple augmentation, the A in the middle of RAG. What is augmentation? Couldn't be easier. The original query is concatenated with the retrieved documents from the vector store, not all 400, but hopefully only 2, to provide an additional context for the generative model. And this is again another LLM. So I know what you're going to ask. If you're a subscriber of this channel, you say, hey, is this comparable to a few-shot example? This in-context learning? Well. And you might also ask, hey, wait a minute. Now let's look at a very specific case that we use here RAG for causal reasoning and decision making. If your task is that the LLM should actively decide something, you need causal reasoning. And if you have now your causal reasoning RAG, it tries to provide now examples of causal reasoning pathways of solutions that are in the vector store in order to generate a blueprint for a new unseen task. And if you have seen my last video, you know it fails. Even if we have GPT-4 Turbo with RAG or we have Gemini 1.5 Pro with RAG, it fails. And now you have the idea, hey, wait a second, but if I now fine-tune my LLM in RAG, so the G1, with causal reasoning instruction dataset, what would happen then? Interesting question, isn't it? So, and here we come to the 9th step for RAG, to generate an output. So the augmented input is processed now by a generative model, and you can choose, you pay for whatever you like, GPT-4, Opus, whatever you go for, to produce the final response, leveraging both the original query and the retrieved and selected additional context, original from the vector store and then re-ranked, and again re-ranked, and we have a coherence LLM. And you see we have a lot of computation to do just to get you the right piece of information. And hopefully your LLM that is now generating this output was trained on this particular level of complex reasoning, because otherwise you provide the augmented input, but the LLM itself is not able to understand this high level of complexity to solve the task. So you see, there are some, let's call it problems that you have to be aware of when you build your RAG system. Now, you have to ask yourself, if you want to optimize the RAG, what element in the RAG system you want to optimize and how it depends on the other elements in the RAG system. For example, you can optimize the first LLM for the data collection. And yes, you get it for the data collection. The very first step that I showed you, you don't do it manually, but we have an LLM that generates here or selects the data or even generates syntactic data for us. So maybe you optimize this LLM. Or you decide, in addition, you optimize the second LLM in our RAG system, where it is deciding on its pre-trained data set about this embedding functionality, remember, with a specific tokenizer and with a specific complexity that this LLM has been trained on. It can now find and build embeddings in a vector space. Of course, you have to make sure that this LLM is really able to cope with the complexity that the data bring in. So it is interesting here about this synchronization and the performance axis of these two LLMs. And yes, you guessed it, and we have a third LLM that takes care about this re-ranker functionality when we have 400 answers coming back from a vector store, because the vector store says, hey, I'm just looking here for a close-by document, but I, as a vector store, have no idea which is the correct answer. This you have to do a re-ranking for. Well, I did not tell you that there is also a fourth LLM if you have the additional step of a coherence validation of the Reranker. So this is only for experts. But then, hey, then you have your fifth LLM for sure. And this is the LLM that generates here the final output from the query that I input, all the augmented documents that we get back. And then the simple output here. This is the responsibility of the fifth LLM. And now you understand that all those LLMs are sensitive because their output is the input to the next one. So if one is missing a kind of a complexity level or is not having here the capacity to understand the domain-specific terms, even if you go with a byte pair encoding tokenizer, you might up in trouble. So you have to decide, if you want to optimize your RAG system, which LLM you want, for example, to fine-tune on new improved data, maybe on instruction tuning. Or I've seen a lot of questions, which LLM do you want to increase the size of the vocabulary to add domain-specific terms? How do you alter this vocabulary? What is the runtime if you have to readjust the LLM to the new vocabulary? And does the vocabulary have to be somehow connected to the other four LLMs? And how is all this happening? So great questions. And then you remember that all of these LLMs you operate with are predefined, not by you, pre-tuned, not by you, and pre-aligned, not by you, and you don't have access to those data, for domain-specific LLMs within your RAG system. So, do you expect any problems arising from this particular fact? And now you understand why it is not the RAG system itself, but it is the weakest element. It is this vector store that is not at all performing. And maybe we should look why there is still this vector store element and why there are millions and millions of dollars spent for marketing and that this stays still in the technology loop today. Of course, if you optimize this, about 2.5 weeks ago I showed you this new discovery that we have retrieval heads in our LLM. So now you can optimize here your specific retrieval heads. And you remember, only about 5% of all your heads in your layers of your transformer architecture of your LLM are retrieval heads who do the actual retrieval. So if you enforce here the power of your retrieval heads, your complete system performance will go up. So you see, we had 9 simple steps, 1 to 9, to explain what is a RAG system and give you also an input here about the latest research how to optimize a RAG system. And on the other side here, this is our Grog Transformer. So you see here the market dynamics and how many people know about RAG and how many people know about Grog Transformer. And there's a reason behind this. If you remember that I tell you vector store and you remember immediately the image that I told you. So let's assume now, if you want to move from RAG over to the new technology, what we can do, what would you say? Maybe you say, hey, I have now this causal reasoning data, or I have new domain knowledge with causal reasoning data, I don't know, chemistry, for example. So what I can do, now if you want to stick with the old technology with RAG, it is simple, no? You provide this new data into your, whatever you call it, body of vectors in a vector store with an index. So you take all your causal reasoning data and you just dump it into the vector store. And Databricks will be happy because they're going to tell you, hey, we have a solution for data lakes. But no, we are not talking about Databricks. We are talking about here the normal RAG system. So now there might be a problem in this, no? Because maybe this new causal reasoning data, who have to be very specific and very domain specific and very maybe even contain out of distribution data, this may include unknown terms, maybe just in the vocabulary that you are happy because we know how to solve this. Or maybe the complexity of your causal reasoning data you provide as a learning material is simply too high for the LLM that generates the embedding for the vector store, because the vector store is generated by an LLM, and maybe this LLM is not powerful enough because, you guessed it, those companies that run the vector store do a profit optimization to embed. Or maybe this LLM simply lacks the ability to reason at all or at your particular level. So you might say, so if I just dump here all my data into this vector store and I have here some LLM that generates here everything, maybe this is not a perfect solution. Now you might argue, wait a minute. I have now the perfect causal reasoning domain-specific dataset. You know what I could do, like we did in the good old times? I could just fine-tune my open source LLM that I know on my specific data that I created here for my domain, and I fine-tune my LLM. And I do not build a vector store. And you can do this, and maybe this video helps you. I show you here the new tricks how to fine-tune your LLM without generating too much hallucination. So in this video, you find some insights how to do this. And you remember, it is all about here where overfitting starts. You train on known data. You have your fine-tuning LLM where you train it on the unknown data. And you have to be careful here from the development accuracy, and all of this is explained in this video. And now I know what you say. You say, hey, the argument of a vector store is I can dump constantly new data in the vector store, by those companies who run the vector stores. Every minute they dump here the new content of, I don't know, the internet, respecting all legal requirements, of course, into the vector store. So this is a huge, let's say, a copy of the internet, just with embeddings. And this costs a lot to maintain and a lot to keep on running. But now imagine for our particular task, we say we don't need everything of the internet. Because if I need, let's say, every hour, an update of my data stream, I can do here, I have an LLM with a function call capability. So I update here, you can even do it continuously, your data stream, and you have access to your own financial database or your own secure server where, I don't know, every 5 milliseconds you have a new financial data coming in. You see, if you have, and this is what I call a dedicated system or an expert system that is maybe focused only on one task, let's say finance analysis, you do not need the contents of the vector store about recipes or what is happening in Hollywood or what is the latest in US policy regarding I don't know what topic. You would have a dedicated, let's say, financial LLM that has an extreme performance, a task-specific optimized LLM. So you see, the question is now, if you say how to optimize RAG, the first question you have to say, do I want really to optimize RAG? Do I really want to put everything in a vector store? Or do I have a more limiting, only focus on finance, solution that is much faster and more performance? Here we have the data for this. You remember in my last video, in part number 3, I showed you here the benchmark data. And we had a Gemini Pro 1.5, and for a direct answer prediction on a causal reasoning task, we had a 28.7 accuracy. And if you went and say, hey, chain of thought, and please verbalize your reasoning step so I can check here, and I follow each reasoning step the LLM tells me, and I validate that this is a correct reasoning step at this particular period of time, then you see the accuracy goes down to 11%. And now you might say, oh, this is the common knowledge of how the vector store people sell their product. And you know, this is interesting because RAG itself is a kind of a simple methodology. It is just if you put the vector store as your only input for RAG, this is where I think the transparency and the simplicity of the system is completely lost. And you depend here on some commercial products, of course. And I understand that this is a business model, and I understand that investors invested hundreds of millions, and I understand that they want to see at least a profit margin of 1,000%. But you have to ask yourself, is it still the time that you use a vector store for your particular AI system? Because look, if we now have this direct answer prediction and we activate a RAG, so we dock on a RAG to our LLM, how does the figure change? Gemini 1.5 Pro from 28 now to 37, which is great. And here we have a chain of thought reasoning here where you verbalized reasoning step, and you can check here step by step if this is correct here with a RAG system. And the RAG system now delivers here, so to speak, here the solution from its vector store knowledge. You see, we go from 11.3% to 12%. So we increase with RAG at 0.7 percentage points. This is the performance that we are talking about, and this is why I call it an old technology. To go from 11% to 12% is not what I personally are looking for in my AI systems. And remember, if we look here at this little unknown field here, the Grog Transformer, we achieve 99.3% performance. So you see, those are the arguments you have to be aware of, and then you make your decision. Great. Now there is, of course, with RAG, you know that there is a problem. Because let's think about in the US, we have upcoming presidential election. Let's see, there is here a very particular person, and you ask for the terms that you think of if you see this person. A, B, C, D, and you write something. Now, if you feed here the content from CNN into your LLM, and you feed the content of Fox Entertainment or whatever they are called into your LLM, the LLM learns real opposite terms for the identical person. And of course, this is how we humans are, and those data are correct. Because this is the business model of those entities. So yeah, this is it. For humans, we understand this, but for an LLM, this can cause some serious problems. Let's make another simple example. Let's say this. What do you say this is? Now, if I put this into a GPT-4 system and I ask what it is, I get, for example, these answers. It's a ball. It's a nuclear fireball. It's a red dot. The explosion is imminent. It's candy, or it's a balloon. So you see the LLM in the second step of RAG. This, if we use GPT-4 for this object, whatever it is, we have a ball that children play with right next to the nuclear fireball, right next to an explosion, right next to candy. And you know what we did as AI researcher? Because we said, hey, this is not okay that we get this as a probabilistic result back from our AI, no? And it is correct. The mathematical operation, that those are real close semantic vector, is a correct mathematical operation because the data we feed in here are really opposite terms. Because, I have to make it clear, some people on the internet are not scientists and they have here some really strange ideas about whatever. But the LLM learns from everybody, everything. And therefore, this incoherent data stream, of course, leads to hallucinations within our LLM. So what we did, we invented a final filter. And we recognized that neither the pre-training nor the fine-tuning ensures here that the LLM adheres here to the human ethical standards. Be polite, be nice, don't hurt anybody with what you say, or specific user preferences. you wanted the answer to a specific topic is always only in this form. So a final filter was invented. And you notice the very old one from OpenAI is reinforcement learning by human feedback. So we have a human feedback collection. The humans sit down, provide a feedback on the model output. Now, this is done today, also by another LLM. The 6th or the 7th LLM in this RAG system, I can't remember. Then we have a reward model training. So we train here a reward model from game theory, predict the human preference based on the feedback. And then we have a policy that we define and a continuous policy optimization if we train now our LLM using this reinforcement learning. And you see, in the 10th step, we kind of override everything that we learned in step 1 to 9 because we don't want what we have in step 1 to 9, the result that comes out of our RAG system. And therefore, we have a final filter that tells us, hey, if this is the query, this is the answer you should give, or this is the form of the answer you should give, and we retrain again completely something. And you as a user, you have no idea what exactly were here the policy and the reward model training parameters. Now, if you want to learn more about here, forget reinforcement learning by human feedback, PPO, then we had the DPO, then we had SFT, supervised fine-tuning, and DPO, and then we had not anymore supervised fine-tuning and DPO, and now we have ORPO, and now we have even more advanced algorithm, but in principle it is all about the same. We don't trust the first 9 steps, so therefore we have a final filter. You see, now you might ask yourself, is this the perfect system configuration? We have 10 steps where each step kind of corrects the step before, and we still have a 12% accuracy performance of this RAG system when we talk about causal reasoning. Okay, great. So you might say, okay, finally I get this with the RAG, but can we finally come here to this new technology? No. Okay? Because I asked here GPT-4, Turbo, Omni, I don't know anymore. I said, hey, what about the limitations that we have now in a vector store? So I learned that it depends on the vocabulary of the generative LLM in the second step, the level of complexity that an LLM can handle at all the different steps, the tokenize of that LLM here at the very beginning, maybe even at the data cleaning or at least in the embedding phase, and how deep the embeddings were constructed and in what kind of layer structure we have of the architecture. Is there anything else? And GPT-4 comes back and says, hey, yeah, there are some topics, you have a vocabulary dependency. We talked about this. A complexity handling problem. We talked about this. The impact of the tokenizer. We talked about this. The embedding depth. We talked about this. The dimensionality of the embeddings. We have not talked about this, but it's clear, because those are high-dimensional vectors, in 1024 dimensions, and there is a connection between a high dimensionality and a level of complexity you can handle if you do not optimize for this particular architecture. Then you have a problem with scalability. You have to take care about the storage and retrieval efficiency. We talked about the data freshness and the updating. Yes, about contextual relevance. I just had one sentence on this. There's a semantic drift over time. Yeah, this is just for experts. And we have a problem with the interpretability, understanding what each dimension in the embedding represents. This is just a black box. So yeah, and you say, hey, only 11 points that we have problems with the vector store. No, of course not. We have number 12 bias here. We have resource requirements. We have integration here. Problem of integrate with other system to have a coherent structure. There are so many things you have to take care of if you have a vector store integrated. It's the main input provider for your RAG system. So I personally can say, from my feeling that I don't like RAG, I have to correct myself. I don't like the vector store in front of a RAG system. I don't like that somebody decided what to put in a vector store where I have no idea what tools they use, what complex LLMs they use, if they just use the cheapest LLMs for them to make the most profit, which I understand is a business model, and I understand without the investors we would not have those vector stores that are not open source. But I think for myself, I say RAG is nice, but can we find something better like a vector store? And yes, of course we can, because this is the next point. So now we cross out a vector store for our RAG. So what we have an LLM with a function calling capability. Almost everything has this in parallel. This is a little bit more complicated. And we can extract here with function calling huge amount of data, even if we time critical and latency and whatever. In about 0.5 seconds, if you have parallel function calling, you get a lot of data back for your augmentation. So function call, or you have a function call to Google itself, to its API, and you get all the results from Google back, or you have multiple dedicated databases you can do, or you can question in parallel. So you are all between less than a second. So beautiful. What's next? Now, have a look at this. We just crossed out the vector store. We have now a very dedicated LLM with function calling. We can connect and get fresh data whenever we want, either from Google or internal databases behind our firewalls. And we are at identical level because now our retrieval process is finished. So our R is finished. And now you need another LLM, where you go with the same one that you have, maybe it's open source, to re-rank the result. We have also 10, 20, maybe also 400 results coming back. And we have to find the best one. Or you concatenate everything together. It's up to you. And the next level is, yes, you augment it. Augment the query with the additional retrieved data from the function calling, let's say the Google or wherever you go, or whatever you have a parallel function calling. So you see, you do not have to pay for a vector store that all the content, let's make a simplification of the complete internet, is now held available for you because maybe you do not need the complete content of the internet, but maybe you have a dedicated LLM for a very specific task. So you see, when I was asked, when should I use RAG today? I would say, if you build an LLM or you have a service where you need an LLM that is everything to everybody at all the time, so you have to cover all the different domains in this world that is available on the internet. And let's say it's 100,000 domains. I have no idea. From recipes about French poetry to traffic news to political news to I don't know what, 125 languages. You can't put this in the pre-training of an LLM, which is not a correct statement because GPT-4 is doing it. And GPT-4 has not an operational RAG system. And GPT-4 gives you this function calling ability. So you see, when do you need a RAG system? I don't know. But there's another point that is really RAG, is really perfect. And this is the speed of the vector store operation. Because if we already have copied the complete, let's say, assume oversimplification, the complete content of the internet, and we have brought it into a vector form that enables us to perform computational efficient mathematical operation on the vectors, and we do not have to go out and search for particular topics on the internet, then this speed of the vector store, and if somebody continuously fills up the latest information from all of the internet into this vector store or dedicated vector store, then this might be a topic. But then you have to make sure that you trust here the operators and the creators of the vector store. You have to see the logs that it is really continuously updated. You have to understand what are their security measures. And if it is really integrating all the dependencies that you need for your particular LLM. So you see, there's currently not an easy topic for a RAG system to survive in this place where they rely here primarily on the vector store as their main input source. And you see, there's an easy alternative. Beautiful. Okay. Yes. Just when I thought I can finally come to the Grog Transformer, no, I want to show you another brand new research from yesterday. So June 6, 2024, we have here Peking University, UC Berkeley, and Stanford University publishing the latest on sort augmented reasoning with LLMs. So you see, the reasoning problem in LLMs is so massive that they have now the buffer of sorts. Beautiful. So you might say, hey, what is a buffer of sorts? Well, it is the latest research. And you see here we have a single query, then we have a multi-query, and now we have the buffer of sorts. Never mind. If you look at the example, and I thought, okay, if this is the buffer of sorts, and it consists of a set of sort templates, and if I look at the sort templates and I see that the template 1 is to solve any quadratic equation of the form, you can follow the general approach, calculate the discriminant, determine the nature of the roots. This is just a solution template for one very specific problem. And then I define, or I let define here, n sort templates. And the totality of all my sort templates form the buffer of sorts that I can now use. So if an LLM is confronted with an input problem and it understands that, I don't know, I have 10,000 sort templates for this particular problem where I have to solve a quadratic equation, I need sort template number 1, and then I'm able to do the reasoning and follow this template to come to the correct conclusion. Now, I personally might think, well, I think we have here also, how to say this? You remember here the compute, it's called a Python environment where we have a code LLM. So we don't need here a template here in verbal where I explain here in detail in the human language how to solve this equation, because I thought we have a code LLM that can do this for us, but no. We now invent the sort template. I mean, UC Berkeley and Stanford invent the sort template, and I call it, just unofficial, it's a solution template for one particular problem. You see, here are all the steps that we do, which I thought we have a code LLM to do this in real time, but who cares? And then in the annex of the document, you see they show here 6 examples of sort templates in 6 different categories. And there you have it, a text comprehension task. You have the task to analyze a table with various attributes of whatever. You have name, age, height, weight here in the table. And then you have to update the entries and have some question to answer. And then in the sort template, and I was smiling, I can't tell you. Then you see, you pause the initial table, you read here the table, you identify the attributes in question, who is the oldest and who is the heaviest and whatever. And then in the sort template, in my solution template, you have the command, apply logical reasoning. The whole idea of this sort template was to solve logical reasoning and be a tool to solve logical reasoning. And now in this tool, you say, hey, apply logical reasoning. UC Berkeley and Stanford, yes, sometimes there's, something going on. Okay, this is the latest research. I personally do not see that I would use this immediately because I'm interested here in this particular step and now that not that I have another template structure. Okay, so whatever it is, you might have now here this dedicated set of sort solution templates with predefined solutions done by, I suppose, another LLM, or maybe even a code LLM in human language available for you now. My goodness. And now, finally, please allow me to come to the Grog Transformer that solves all of this. And now we're here with the Grog Transformer, and yes, I have 3 videos here. Grogging LLMs, structured grogging, and grogging versus RAG performance benchmarks. And yes, those Grog Transformers solve here all our problems that we had here, that we just went through with RAG. Beautiful. So remember, we have an 8-layer transformer that might be open source, I would recommend it, that outperforms on a GPT-4 Turbo plus RAG in a causal reasoning task. Isn't that beautiful? We have, of course, now to pre-train the system till these generalizing circuits emerge within our architecture of our transformer layer. And we have to take care here about a specific invert to atomic ratio, where I showed you in video number 2 how important it is to have the perfect data set and the perfect ratio of the data set. And of course, we have to design and build here specific domain-specific causal reasoning data sets that are optimized for an early and effective grogging phase transition to set in the transformer architecture when it is continuously learning. So you see, to build a Grog Transformer is not that easy, but if we master this task, we can get rid of all the problems that we have. So let's look at Grog Transformer. Again, I just want to really stress this. A Grog Transformer is not everything for everybody. I see it primarily as an LLM for a specific task where it is close to perfection. For example, an LLM for a risk assessment of an insurance company. As a company, I have all the data from the last 10 years from all my customers, all the events that happened, all the connection between the events. I understand why it happened. I have all the rulings, maybe the legal rulings. I have all the decisions that I took within my company that form here my knowledge base for the company. I have all my argumentation that I confront my clients with, and I have all the patterns, how I behave and why I behave as a company. So this is, of course, here the perfect pre-training data set for grogging. So I have this data and I can start now to design a data set particular for the grogging phase of my LLM. And then if I have this system, and let's say I have monthly new data about new global change induced events that are happening within my region, I develop or I find that new patterns emerge, that maybe new time scale emerge here. So this is beautiful because monthly I can maybe run a fine-tuning on a particular fine-tuned data set, particular optimized here for the grogging phase of my transformer. And then if I really have exceptional unique events, let's say on a particular day or maybe even daily, so where new patterns emerge, new timescales are here, but within my domain of risk assessment, then I can use here in context learning in my prompt structure itself. And this is beautiful because my LLM is already operating in the perfect grogging phase with 99% accuracy on causal reasoning tasks. So this is how I imagine a dedicated LLM. So I hope you get a feeling from what I'm talking about. Great. Yeah, to do for me. Hey, I have to ask Apple here for an AI MacBook for a month. Maybe they rent it out for a month because I want to build a Grog Transformer here on an Apple MacBook because I simply need the memory for continuous training. 192 gigabytes of VRAM would be nice. The second point is timescale. And coming now from this insurance company example, I'm looking here more in my domain-specific thing, and I thought, how would I build a Grog Transformer? What are the conditions? I thought I would start to pre-train an 8 to 12 layer transformer, I would choose an open source transformer with a causal reasoning dataset in physics or chemistry or whatever science that you need till the grogging phase transition sets in my transformer architecture like I showed you in my last 3 videos. So, for example, I would have here for a complex chemical reaction, this example 1, a pattern example or different pathways, and you understand here the general schema that I use to learn here how and what is the pattern for specific chemical reactions. Maybe I would break it down even to a more molecular level, even talk about here the specific theoretical applications here. But this is just as a demonstration. So of course you have to watch out for the correct ratio of inferred to atomic knowledge data, as I've shown you in video 2. And this is a costly exercise, yeah. So I think if you're a company interested in this, maybe you do it once every year. So you at first, you start here with your established body of knowledge, and this is your pre-trained model that has the level of complexity in its pre-training data that you need. And then, let's say, you do the fine-tuning of this open source transformer with an advanced causal reasoning dataset, till now also for the fine-tuned model, the grogging phase sets in. And now you have more complex things, but based on the pre-trained, the system is now not an out of distribution, but into the domain that it was originally pre-trained on. So you see, it is a dedicated, let's say, chemical LLM. If you ask this system a recipe for a cherry pie, it will not be able to do this, but it will reach a causal reasoning performance maybe of 90% on this domain, chemistry. And you bring in newly discovered patterns into your LLM that were, I don't know, published here in the last month in the research database, research publication. And then again, if you have very specific in-context learning here, you also do this because you have here the grogging phase already in your LLM. Now, this is still heavy research because, think about it, you have an LLM that has now been fine-tuned and is now operating in its grogging phase transition for in-distribution and out-of-distribution topics. And now you have in-context learning this beautiful long prompt of 10 million tokens that you can learn or provide many short examples in addition to an LLM that is in a grogging phase. And now the question is, if I provide an in-context learning plus this 1 million plus million token context length, so many examples will the LLM fall out of its grogging phase, or how do I have to design this in-context learning many short examples, maybe similar to the pre-training dataset, maybe coherent with the fine-tuning dataset form and functions, that this in-context learning still stays within the grogging phase, so that I do not have a phase transition that I fall back to another phase in the system. This is something that is not trivial, and I'm currently running quite some clusters here, some experiments, but yeah, I have not the time, not the resources, and not the money to accelerate this in any form. So this is here my bleeding edge of research that I'm doing currently, where I investigate, hey, if I have a grogged LLM, how sensitive is it now to new in-context learning, many short examples, and what is the performance? Can I even increase it, and on what conditions can I increase it? So you see, it is not a simple topic, and sometimes I think, my goodness, what am I doing here? No? But then, if I get all the questions from you and I'm able, hopefully, to explain some of them, you know, I think, hey, this is just another challenge that we have here in artificial intelligence. And isn't it fascinating that we still have here new research frontiers that we can discover, that we can explore. And then I'm absolutely optimistic that maybe I see you in my next video.